stretching, kids, so I'm wide awake for when we talk about Z-scores. What? Z-scores. What? By the way, all of this stuff can be found at www.nkinfinity.com. All of it's nice and organized. Of course, you know that's N for Newman, K for Krause, or in the next hour or whatever this is going to take, because it's so much fun. I can't wait to finish it. Thank you. It's empty. Now it's going to be a miserable hour. You guys are in for it. I might have to go get another cup. Anyway, let's talk about Z-scores. Well, let's not first. Let's talk about normal distributions first. So it says here, 400 juniors in Hilton took the ACT a few months back, and the results were just released in the school. The scores were normally distributed. That's important. As soon as I see the words normally distributed, I can draw in the normal distribution curve. Until then, not able to do that. With a mean of 24 and a standard deviation of 4. So let's go 28, 32, 36. Now, since the highest score is 36, that's pretty good. It ended there. This is 20, 16, and 12. I guess you don't want to be down in the 12 range. Now, I have no idea if these are accurate, but that's what we want. So we want what percentage of scores are between 20 and 28. That's one standard deviation up. That's one standard deviation down. That's 68.2. Between 16 and 32, that's two standard deviations up, two standard deviations down. You should remember from yesterday, that's 95.4%. 16 and 28. Now we're getting a little funky. Now I'm going to do it. I'm going to do this the hard way and then the easy way. I'm going to use my calculator. 16 and 28. So I need to go all between those two. Well, if I remember correctly, this is 34.1. And this is 34.1. This part I'm not sure about. Let me go back to yesterday. And let's see. So I got all these, but I need these two, which is another 9.2 and 4.4. So I better grab my calculator. So 68.2 plus, I forgot what it was, 9.2 and 4.4? 9.2 plus 4.4. Enter. 81.8%. So let's go back to here. 81.8%. Now the rest of them, well, I'm going to practice, and then the rest of them I'm just going to use my calculator for. So let's go back over. No, I don't need that. Calculator. So menu 652, right? Normal CDF. So in this case, I want to check my last one just to make sure that I was right. And the last one said between 16 and 28 with a mu of 24 and a standard deviation of 4. And I click OK. 81.85. So that's really 81.6. 81.8. 81.8 is all I wanted, 81.8. So it's really 81.8, and then we got a 5 here, so it's really 81.9, but we'll leave it as 81.8. That's fine. Less than 12. So we'll go menu, statistics is 6, distributions is 5, and we want the normal CDF is 2, 652. So what did we say? We said less than 12. Less than 12 means that I want this to be negative 9, tons of nines. I want this to be 12, 24, and 4. And we should end up with 0.1%, 0.001, but that's 1%, right? That's 0.1%. You got to move the decimal place over here. So that would be a little tricky one there. So that's 0.1%. You know, as a decimal, that's 0.001. Greater than 24. Well, greater than 24, that's easy. That's just 50%. All right. So between 24 and 28, that's 34.1%. Now, this is approximately how many juniors scored there. Well, there were 400 juniors, and I'm going to multiply by 0.341. So we'll take our calculator, 400 times 0.341. Oops, enter. 400 times 0.341, enter, and I get 136.4, so about 136. Between 20 and 28, well, we said that was 68.2, so we'll take 400, and we'll multiply by 0.682. Remember, that's a percentage, right? This is percent. So you got to be careful. You got to do it as a decimal. So you can either give me those numbers as a percent or as a decimal. It doesn't really matter. 400 times 0.682. 272.8, so we'll go 273. Between 24 and 32, that I didn't figure out yet, so let's figure out what that is. I can just use my calculator. Menu 652. And I want between, what did they say, 24 and 32? 24, 32, 24, and 4. I'll click OK. And that's 0.4772. So I'm going to take 400 and I'm going to multiply by 0.477 times this. And I get 190.89, so we'll go 191. And finally, between, oh no, not finally, 16 and 20. 16 and 20 is this part right here. So I got to do that again. Menu 652, between 16 and 20, 24 and 4. We got 0.1359, so we're going to take 400 and we're going to multiply it by that. And I get 54.36, so 400, first of all, I should show my work, 0.1359. And I get 54.3, so that's 54. Remember, these are students. These aren't percentage. These are the number of students. So I'm taking the 400 students I was given and multiplying by the percentage. Now, higher than 32. So I'm going to take 400, and I don't know what I got to multiply by, but I want higher than 32. So menu 652. Higher than what? Higher than 32. So 32 is the lowest bound. Higher is going to be a lot of 9. There's a whole bunch of 9s. Put as many 9s as you want. 24 and 4. And I click OK. And I get 0.0227. 0.0227 times 400. And I get 9.1. So approximately 9 students scored higher than 32. All right, so there's we go. That's the stuff from yesterday. So let's talk about something. Let's suppose, and let's go back to the fact that this was the curve from above. So what I want to do is I want to label the normal curve just as I did above. So that was 24, 28, 32, 36. 20, 16, and 12. But now I'm going to create a standard deviation of 2. So I want to superimpose a normal distribution curve that has the same mean, but now the normal distribution or the standard deviation is 2. So instead of it being 4 now, it's going to be 2. So let me pick a different color. So now one standard deviation would be 2, 22, and 26. 2 standard deviations would be out here at 20 and 28. And 3 standard deviations will be out here at 30 and 18. So what's this one going to look like? Well, still the mean score is still going to be right here. But I'm going to have more kids between 26 and... So what I need to do is do this. So here's the tails down here at the end. I probably should, let me just do this. It wasn't a very good one because I should start right here. All right, something like that. Not really happy about that drawing either. So let's try it one more time. This is going to be better. It's going this other direction that's hard. There we go. There we go. So this would be the normal distribution with x bar of 24 and a sigma of 2, a standard deviation of 2. That's the red one. The black one has the standard deviation, so the black one, or the black curve, has an x bar of 24 and a standard deviation of 4. Well, what do you notice about the red curve as opposed to the black curve? You'll notice that the red curve is more, you know what, I'm still not loving this red curve. So let me try this. I'm going to make it look a little bit better. I think I got a better idea how this one's going to look. So I think it should look more like this. So what do you notice? It took the other curve and kind of squished it in, and it reduced the standard deviation in half, which means that between 22 and 26, I'm going to have 68.2%. And then one more standard deviation out, and then one more standard deviation out. But it squeezed it, so it made it more compact. That means more kids are here. And we're going to talk about what a score of 30 here means as opposed to a score of 30 using the black curve. Now this one I screwed up a little bit. I want to do that same thing. I want to superimpose a curve. But this time I'm going to use, let me do this in, let's go green. I want to do an x bar, again, of 24. But this time I want to do a sigma of 8. Well, before I do that, I'm going to go back to labeling my curve the way I had originally in purple. 24, 28, 32, 36, 20, 16, and 12. So now I'm going to label it in green. I'm going to label a curve that has a mean of 24, but now its first standard deviation is going to be 8. So that's one standard deviation down here at 32. And one standard deviation down here at 30 or at 16. Now two standard deviations would be up here at 40. Now since the PSAT doesn't even go above 40, that doesn't even make any sense. And then down 40 would be, let's see, down 8 would be down at 8. And then I go up another 8, so now I would be at 48. And down here at a score of 0. So now the green is going to represent a normal distribution, but with a mean of 24 and a standard deviation of 8. So that's going to kind of look like this. Something like that. Well, what do you notice? The black curve is a normal distribution, and then if I shrink the standard deviation to 2, I squeeze everything in. And I'm not liking this green one again. This is kind of hard to do. That's better. That's better. So I squeeze everything in. Or the green one, since the standard deviation is 8, I'm taking everything and spreading it out, spreading it out, spreading it out, spreading it out. Well, that's the thing we're going to talk about today and why that's sometimes sort of a problem. So what we want to do is we would like to take these and normalize them. Get them to so that we can use the same chart for the same exact distribution, no matter what it is. Well, no matter what it is, we're going to use the same table no matter what. So I don't have to create a table for, I don't have to create a normal distribution for 24 and 2. I don't have to create a normal distribution for 24 and 4, or a normal distribution for an x bar of 24 and a standard deviation of 8. I want to get that so that I can create just one table or one chart in order to look this things up. Because up until now, we've just used the normal distribution curve, but we are going to now start to talk about z-scores and So it's a normal distribution, another way to find the percentage. So z-scores, the definition of z-scores are the number of standard deviations a data or value of observations point is from the mean. So if we're working with the normal distribution curve, that's fine. But sometimes we want to do more than just summarize a group of scores. Most of the time we want to discuss a particular score within a group. Oftentimes we need to answer the question, is the score above or below the average? Other times we're asking how far away the score is from the average. The huge advantages to z-scores is we want to compare scores with different groups of data. So if I want to compare the scores of how you did on this test with the scores on how you did this test, but this one has a standard deviation of 8 and a mean of 26, and this one's got a mean of 38 and a standard deviation of 4, how do I compare those? Because that's this graph and that's this graph, and I want to compare how well I did, but the data is completely different, right? So how do I say, oh, on this test I got a 38 and the standard deviation, was this score, and this one, the score, I got a 55 and the standard deviation was this. How do I compare them? It's like comparing apples to oranges. I can't do it. So what we do is we take them and we normalize them, and we're going to give them z-scores. And a z-score, no matter if you're working with this test, which has a different mean than this test, the z-score will mean the same thing. So a z-score the score is equal to the group mean. So if you have a z-score of 0, then the score is equal to the mean. So let's say you got, on test A, you got a 20, and on test B, you got a 30. Well, did you do better? I don't know. What if the mean score on test A was a 20 and you got a 20? Okay, you were 0 standard deviations above the mean. And the mean score on the second test was 30, and you got a 30. Oh, you got a mean score you got a z-score of 0, which means you got exactly the average. So you didn't do any better in terms of how the entire group did. Okay, you still got that same you got a z-score of 0, which means you nailed it right on the mean on both tests. Let's say I got a mean score that is positive, or a z-score that is positive. That means the score is above the group mean. Well, if I got a z-score that's negative, that means the z-score is below the mean. When the z-score is plus 1 standard deviation, I'm sorry. What did I put here? If I got a z-score of 1, that means it's 1 standard deviation above the group mean. If I got a score of 2, that's 2 standard deviations above the group mean. If I got a z-score of -1 or -2, those are z-scores above and below the standard deviation. My notes here are a little bit messed up. Sorry about that. So how are z-scores going to help us out? Hold on. Let me see if I can come back in a second. So Z-scores are going to help us calculate the probability of a score occurring within our normal distribution. You'll be able to, and the big one is you'll be able to compare two scores that are from different normal distributions. And the other big thing is it standardizes scores from different groups. So as we go through these problems, you're going to see how you're going to be able to compare different groups. And it's going to take you a little bit of time, so bear with it. You'll see that this is really the only way to handle it and the easiest way to handle comparing different groups of data that really have nothing to do with each other, but you can compare them. You'll see. So why use Z-scores? You saw from the previous page, where's my pointer? Okay. That the normal distribution curve would, I'm having a hard time with my thing here. All right. Just keeps, there it is. I'm going to leave it. Maybe I'm not. I want it to go down. Okay, there it is. So you saw from the previous page that when we graphed the normal distributions, the chart looked different depending on what the mean and standard deviation was. The good thing about Z-scores is the chart will always look the same, but we're gonna standardize the numbers that we actually put on it. So take a look. These were the charts we had before. We had a mean of 24 and a standard deviation of 4. We had a nice normal distribution curve. When I shrunk the standard deviation to 2, it compacted the whole thing. And when I increased it to 8, it stretched it out. So you're always constantly having to draw different curves. So what we're going to do is we're going to take these scores and we're going to create Z-scores from them. And how's that done? Well, we're going to use this formula here where, and hopefully you can read that, Z is going to be our score. X bar is the measured number that we're looking for. Mu is the mu is the population mean. And sigma, why don't I have that on that list? Why is that missing? Sigma is obviously our standard deviation, our population standard deviation. You'd think I would have put that in this little thing here because that's kind of important. I wonder if it's just it's sort of not even on there. That's so weird. And it's not even on the right page. So what we're going to do is we're going to use this formula, which I'm going to copy over here. Z is equal to your measured value, X. Notice it's not X bar. It's just X, where it's just whatever observed value we have, minus the standard deviation of mu. That's the population standard deviation, all over the population mean, standard sigma. So we're going to convert these to Z-scores. So we're going to see how a score of 32 did on this test. So we're going to take 32. We're going to subtract 24, and we're going to divide by 4. Well, that's 8 divided by 4, which is a Z-score of 2. So you scored 2 standard deviations above the mean. No longer do we need to worry about 32. It's just a Z-score of 2. How about a Z-score when you got a 34? So we're going to go 34 minus 24 divided by 4, and you get a Z-score of 2.5. So that's 2.5 standard deviations above the mean. Now, here is the situation where we got a mean of 24 and a standard deviation of 2. So this person scored 2 standard deviations above the mean. This person scored 2.5 standard deviations above the mean. Let's see what a score of 32 in this scenario looks like. So we'll take 32 and we'll subtract 24 and we'll divide by 2. So again, we get 8, but in this case we're going to divide by 2. Now this person, this is 4 standard deviations above the mean. They're like in that freaky way out there. You did so good, it's crazy good. Whereas this person scored 2 standard deviations above the mean. This one scored 4 standard deviations above the mean. So a score of 32 on this test is light years ahead of a score of 32 on this test. Even though they got the same number, as in comparison to the entire group or population, this person crushed it. This person did better than average, much better than average, but they didn't crush it. This person would actually be an outlier. And a score of 34, see, 2.5, isn't that close to being an outlier in a normal distribution? Let's see what a score of 34 on this particular test did. 34 minus 24 over 2, that's going to be 10 over 2, which is 5 standard deviations above the mean. 5 standard deviation of the mean is kind of like finding the rarest diamond that you could ever find in a cave that doesn't even exist. That's how far 5 is. 5 is ridiculously way outside the mean. So while this person scored almost close to being an outlier, this person scored an outlier on steroids. Even though, if we look at it, the two tests had the same average, even though the two tests had the same average, getting a score of 32 or a score of 34 on this test is so far above this one. Now let's talk about this person. This person, took a test. The average was 24, but the population standard deviation was 8. Let's see how they did. Oh, okay, so we'll take 32. We'll subtract 24, and we'll divide by 8. Well, that's 8 divided by 8. They only scored in 1 standard deviation above. They just did sort of better than the average. They did better than the average, but just sort of better than the average, not a lot better than the average. This person, let's take 34, and we'll subtract off 24, and we'll divide by 8. This is 10 divided by 8, which is 1.125 standard deviations. So again, this person scored slightly above 1 standard deviation. So they're sort of better, but not crazy better. Now let me remind you, let's go back to this population standard deviation. Let's say we had that 24 here, and we go up 2.5 standard deviations. That's here, right? 1 standard deviation is here. So that person that got a z-score of 1 is, okay, they did better. The person that did 2.5, they did better. 5 is over here. Plus 5 standard deviations? That's ridiculously better. Think about it. There's nobody down there. There's nothing. The chances that it happening is like 0. So, if you're not getting it yet, we're going to keep working on it. Let's try a few problems. Let me pause this for a second. Okay, let's see how we can figure this out. Emma just got her score back on her latest math test. She got an 80%. She had no idea if this was good. Right, if you've ever been in a test and I said, oh, you got a 90%, but everybody did better than you, then you'd say, no, that's not very good. Or if you got an 80%, but you were the top scorer in the class, you'd say, oh, okay, that's great. Everybody did worse than me. Now, some of you are like, oh, okay, 80%, that's not good. But if you got the highest grade in the class, you'd be like, all right, I got an 80%, but I got the highest grade in the class. That's really good. I did the best in the class. And maybe the teacher will curve it or something. I don't know. But I don't know how do you compare it? Okay, so I'm going to say, she didn't know if it was a good score. So she said the teacher said that the average was 76%. So, okay, you know that you beat the average. Now, that still's not going to tell me. I don't know how I did. Even if I know the average, the only thing I can say is, okay, I beat the average. But I still don't know how I did. Still don't know how I did. Did I do remarkably better? Did I do a little bit better? So what other information do I need? I need the standard deviation. I need to know how spread out the data is. This is key to figuring out how well you did. So let's assume that the part you needed was that the standard deviation was 2.2. Okay. So we are going to turn this into a z-score. So z equals, she got an 80, 76% was the mean, and 2.2 was here. Now, if I do that math, I'm going to end up with 1.82 as my z-score. Now, somewhere, hopefully in your packet, there's a z-table. And I need to figure out where 1.82. I scored 1.82 standard deviations above the mean. So there's my z-score. My z-score is 1.82. I'm going to look that up. .82. There's 1.80, 1.81, 1.82. So the answer is 96.56. So, in other words, where do my, oh, I got to go back. Just got to go back here. If I look that z-score up, then she scored, so we look it up, we got a 1.82. She scored, so we look up the z-score of, so the probability that the scores are less than 1.82 is 0.9656. That's what we just looked up. Well, what does that mean? That means she beat 96.56% of the kids that took the test. So she crushed it. Even though she only got an 80, she beat 97% of the kids that took the test. But what if the teacher said, okay, wait a second. Actually, the standard deviation was 8.5%. You say, okay, we'll take a z-score of 80 over 76. And this time we're going to divide by 8.5%. And in this case, we get 0.47. So, okay, go back to my table. I'm going to look up 0.47 now as a standard deviation, 0.47. Laundry's done. 0.47, 0.4 and 7, 0.47, 68.8%. So in this case, I keep forgetting I got to just go back up here. If I look that score up, I get, so in this case, what I get the score, so the probability that z is less than or equal to 0.47 is 0.608, something like that, right? Well, what does that mean? Well, she beat 68% of the kids taking test. So, yeah, she did better than the average, but not much better. That means not much better. In my house, you'd say 32% of the class beat you. So you can see where the standard deviation is going to make a huge difference depending on what our score is going to be. All right, so let's practice some more. According to the Buckert and Howell research firm, the time spent by kids researching or watching television per year can be modeled by a normal distribution with a mean score of 1,200 hours. What percent of the kids watch less than 1,000 hours? So what we're going to practice doing is labeling our diagram. So we've got a X bar. This is my Z score of 0. So what we're going to do is convert this to a Z. So we're going to take we got a mean score of 1,000 hours and a standard deviation of 180 hours. So we're going to turn this into a Z score. What percent of kids watch television for less than 1,000 hours? So we're going to take, that's our X value. We're going to subtract off 1,200. And we're going to divide by 180. So if I do that, that mathematically turns out to be negative 1.11. So negative means we're going this way. So my z-score is negative 1.11. And I want less. So I want to shade this. I want to get used to shading this. Now notice this thing's all symmetrical. So whether or not I found that tail or I found the tail on the right, it really doesn't matter. As a matter of fact, the only chart we're going to give you is this negative chart. The chart where the tail's on the left. And you're going to have to start figuring some stuff out. So we want to go look up negative 1. So we want the probability that our z-score is less than or equal to negative 110. And we're going to go look that up. So we go back to our table. Negative 110 right there. Negative 110. 0.1357. So go back up. 0.1357. Well, what does that mean? That means, oh, I looked up the wrong one. I looked up 0.130. This is 0.1311. Negative 0.11. 1335. Doggone it. Shoot. So 0.1335. So what percent of kids watch for less than 13.4% of kids watch less than 1,000 hours. All right. So again, what we want to do is label our diagram, and we want to figure out what's going on here. So this is going to be 0, z-score of 0. We got to convert to a z-score. Same work, but this time our measured value is 1,500. We're going to subtract off 1,200, which was the mu, and divide by our population standard deviation, which is 180, and we're going to find out that this is 1.67 standard deviations. Now this is positive, so we want over here sigma, and we're going to go 1.67 standard deviations above. So we want more than, so we want this tail. Now what I'm going to show you is this. It doesn't matter which table we look at. I'm only going to look at this negative tail, because it really doesn't matter if I check out this tail, because this area will be the same as this area. This will be the same z-score. In this case, the z is negative. In this case, the z is positive. So they're symmetrical. So really, I only need to look up 1.67. Whether it's positive or negative makes no difference. 1.67. Let's see, that's 987 right there. Right? Is that 1.67? 1.67. So 0.0475. 0.0475. Remember, that's this tail right here. 0.0475. That means about what, 5%? So if I go back up here and I say, okay, the probability that z is greater than or equal to 1.67 is, and we looked it up, 0.0475, or approximately 4.75% of kids watch more than 1,500 hours. So now this one is going to be very, very tricky. I want the percent of kids that watch between 1,000 and 1,500 hours. So how are we going to do that? What percent of kids watch between 1,000 and 1,500 hours? Well, 1,000 is here, and 1500 is here. Maybe what we want to do is to label this 1000 and 1500. And we want to know what this is. We're going to convert these to z-scores. Now, I already did their z-scores, right, for these. This is the 1000 has a z-score of negative 1.11. And the 1500 has a z-score of 1.67. So I want the probability my z-score is between negative 1.11 less than or equal to z less than or equal to 1.67. How am I going to do that? Well, I've already looked up this area, which we found out to be, if I look back, this is 13.35%. And I already looked up this much, which was 4.75%. Well, if the total area of the curve is still 100%, correct? Still 100%, then all I got to do is take 100, subtract off the 13.35 I already found, subtract off the 4.75 I found, and I find out that is going to be 81.90%. So 81.90% kids watch between 1,000 and 1,500 hours. All right, let's keep going. All right, for those of you that don't know, because you haven't been following me at all, I own a Chevy Volt. And General Motors claims that the Volt's owners average 850 miles per gallon with a standard deviation of 80. What percent of people average more than 950 miles per gallon? All right, so if this is my X bar of 850, and I want a standard deviation of 950, I got to figure out what z-score that is, because this is a z-score of 0. I want to figure out what my z-score is. So I take my z and I go 950 minus 850 divided by 80. Well, that's 100 divided by 80, which is 1.25, 1.2. Yeah, 1.2. 1.20. So, again, I want to know this. Now, whether or not I know this tail or I know this tail, it really doesn't matter. I got a z-score of 1.20. Now, I'm going to show you this real quick. Whether I look up negative 1.20 or positive 1.20, see, that's a little confusing right there. That says 88.9%. But remember, looking up in the positive one is really adding up all of this. I don't want this. I want what's in this tail here. So this chart, although sometimes you'll see it, we're really not going to use this chart. Because we want to get used to, because this is how our AP Stats teacher does it, and this is how I think we should do it as well, we want to just get used to looking up the data in the tails. Because if we can find the data in the tails, we're fine. So these tables always tell you the number and to the left. So we want to look up in the tails. So we always want to look just this. So I'm looking up a z-score of negative 1.20, which is a 0.1151, which is this part right here, 0.1151. So the probability that z is greater than or equal to 1.20 is 0.1151, or which is equal to 11.51%, is the answer. Well, what percent average between 800 and 1,000? So we're going to go between 800. Wait, what's the number? The middle is 80, right? 850. Okay, so let's make this accurate. The middle is 800 or 850. So we're going to go 800 to 1,000. Well, what we want to do is convert each of those to a z-score. So we need two z-scores. So 800 minus 850 over 80. That's negative 80 over, that's negative 50 over 80, which is, and I've already figured this out, calculated this out, negative 0.63. We also need a z-score for the 1,000, so that's 1,000 minus 850 over 80, which is 1.88. Now, we're going to look these up, and we're just going to find the tail values. Now, this is what I want. I want in between here, right? But what I'm going to do is I'm going to look up this, and I'm going to look up this, and I'm going to subtract those off from 1. So I want to find those two values. So here's how we're going to do it. We're going to go look these up. We need a z-score of negative 0.63. We're booking negative 0.060123. There it is. 0.2643. Oh, wait, hold on. Yes. 0.2643. So 0.2643. And if I look up 188, again, I'm going to look up just here. I only care about this negative, 188. And 188 is right here. 0.0301. 0.0301. So here is 0.0301, the tails. I know it was giving me the left tail, but it doesn't matter. They're symmetrical. And this tail is 0.2643. And that makes sense. This is 26%. This is about 3%. So I'm going to take 1, and I'm going to subtract off 0.2643, and I'm going to subtract off this tail. So we're just subtracting off the tails. And when I do that, I get 0.7056. So approximately 70.56% of all Chevy Volt drivers will get somewhere between 800 and 1,000 miles per gallon. So I've driven my Chevy Volt now, and this is actually very accurate, although up until now, for 3 years. I have 33,000 miles on my car, which really doesn't make any difference. And I claim to have used only 27 gallons of gas. Oh, well, hold on a second. Which percentile does his drive him, what? In which percentile does his drive him land in? I don't even know what that says. I want to know what percent of all drivers drive and get as good a gas mileage as I get. So the first thing I got to do is figure out what my gas mileage is. So I'm going to take 33,000 and I'm going to divide by 27. And that gets me 1,222.22 miles per gallon. Well, we know that the average is 850. So that's going to put me up here somewhere. 122.22, and I want to figure out what percentage this is, because these are the people that beat me, and I beat all of these people. But I want to figure out what this tail is, so I got to figure out what that z-score is. 1,222.22 minus 850 divided by my standard deviation of 80, and I get a z-score of 4.65. So I want to figure out what is the probability that z is greater than or equal to 4.65. Well, you already should know the answer to this. That's freaky good, right? Because 3 is barely on the chart anymore. In fact, as a matter of fact, if I go over here, and I can't even look up a z-score of 4.65. Right? 4.6, anything bigger than it, 0.000, this is 100%. So theoretically, I have beat 100%. This is 1.00. I have beat 100% of the people driving a Chevy Volt with my crazy good driving. All right, that's kind of hard to understand. We got one last problem, I think. Well, we got two last problems. Why does that say 10 and this says 4? Suppose. All right, I don't know. We'll come back. All right, let's see how we did. Suppose that the weights of M&Ms in a 3-pound bag are normally distributed with a mean of 46 ounces and a standard of 1.2. So mean is 46, which is a z-score of 0. And we got a standard deviation, we should write right here, 1.2. Get in the habit of writing the mean on there and the standard deviation right there. What percent of M&M bags weigh more than 47.5 ounces? So we got to convert that to a z-score. So we're going to do 47. So wait, 47.5 should be somewhere around here. And so we want that tail. We want way more than, so we need that tail right there. So do 47.5. We're going to subtract off 46. And we're going to divide by 1.2. Well, if I do that math in my calculator, I get 1.25 standard deviations. So 1.25 standard deviations. So this score, or this weight of 47.5 is 1.25 standard deviations. We're only going to look at the negative. 0, 1, 2, 3, 4, 5. 0.1056. So this is 0.1056. So the probability that Z is greater than or equal to 1.25 is equal to 0.1056, or approximately 10.5%, 56% of bags weigh more than 47.5 ounces. Wegmans refuses any bags that are sent with less than 43 ounces. So again, our mean is, what did we say our mean was? Our mean is 46. Wegmans is going to send back anything less than 43. So anything down here, we refuse. Wegmans is going to refuse. So we got to figure out how many bags or what percentage of bags approximately Wegmans is going to refuse. Well, the first thing we got to do is figure out what percent of bags are going to come with less than 43 ounces. So we got to convert that to a z-score. 43 minus 46 divided by 1.2. This is our z-score. And we get a z-score of negative 2.5. So you can see right now that's not going to be very likely. So we want the probability that Z is less than or equal to negative 2.5. Negative 2.50 is right there, 0.0062. So this is equal to 0.0062. That's not even close. 0.0062. But that's not the question that was asked. The question that was asked was, how many bags of the 800 will Wegmans refuse? I got to take 800 and multiply it by 0.0062, and I get so 0.0062 times 800. Enter. 4.96. So Wegmans will refuse about 5 bags. All right, we got one last one. I always take the twins. Got Tessa and Tierra. So the average SAT score for Hilton High School is 520 with a standard deviation of 65 points. The average reading score for Hilton is 500 with a standard deviation of 80 points. The College Board states that the scores are normally distributed. That's important. Tessa and Tierra in an argument. Tessa says that her score of 600 is her math score of 600 is better than Tierra's verbal score of 600. Well, wait a second. They both got a 600. Then they both did equally as well. that's not the case. That is not the case. Math has a different set of parameters than verbal. So how do we compare them? There's no way to compare them unless we normalize them and put them back on and z-score them. So what we're going to do is create z-scores. We got to see who's right. So let's talk about Tessa. Tessa got a 600 on math. Well, this is math, so we're going to deal with math first. The math average is 520 with a standard deviation of 65 points. So the math average is 520 with a standard deviation of 65. Tessa got a 600, so she's up here somewhere. So let's convert this to a z-score. A z-score of 600, that's Tessa's score, minus 520, which is the average, divided by 65. Well, if we do that mathematics, that z-score is 1.23. Okay, let's talk about Tiara's verbal score. Verbal has an average of 500. Tiara got a 600. And on this standard deviation is 80. All right, so let's convert her 600 to a z-score, because we can't compare the 600 to the 600, but if I normalize them, I can compare z-score to z-score. 600 minus 500 divided by 80. Well, if I compare that, I get a z-score of 1.25. So now I can compare them. Tessa is 1.23 standard deviations above the mean. Tiara is 1.25 standard deviations above the mean. So I don't even have to go to the table. I can just compare these. Because Tiara's z-score is higher than Tessa's, Tiara did better on the English test than Tessa did. So Tiara did better on the English test than Tessa did on the math test. Now, if you want to figure out what their probabilities are and figure out what percent she beat, we got to figure out what z is greater than or equal to 1.23. So we're going to figure out what this is. So we're going to go look up 1.23 and 1.25. So 1.23 0123 is 1.23 is 10.93. Shoot. 10.93. 0.1093. So Tiara's, we did 1.25 just a second ago. What was that? 1.25 was 0.1056. Now remember, these are the tails, 0.1056, 0.1093. So to figure out how many percent she beat, we're going to take 1 minus 0.1093. 1 minus 0.1093. And she scored in the 98th percentile. She scored in the 98th percentile. Oh, wait a second. We better be a little bit more accurate. She scored in the 98.07th percentile. And we take 1 minus 0.1056. She scored... Oh, yeah, okay. I screwed that up. I knew that was a little high. 1 minus 0.1093. So she scored in the 89.07th percentile, whereas Tiara scored in the 89.44th percentile. So in other words, pretty much they did the exact same thing, but because Tiara's score is slightly higher, Tiara did slightly better on the test. Later on, I'm going to show you examples where they're going to be drastically different. Even though they might have the same average, or they might have gotten the same score, they're going to be drastically different as far as how far away they are from the norm. Okay, I hope you got a little bit of idea about z-scores. Don't worry, we're going to practice z-scores some more tomorrow. Okay, so they're going to keep practicing them. All right, kids. Adios, amigos.